So the reason for this, of course, is that that we always have what we usually refer to as random variation, and what we typically mean with that is that in this context is that we don't only have variation that's caused by people being in different groups, but we also have variation between individuals within a group. And of course, if you have a lot of variation within individuals in a single group, then by chance you will also find differences at a group level. So that's why we usually look at confidence intervals or error bars on the means before we make any judgment about whether something is going on or not. So if the situation would look like this, then most of us would probably be very hesitant to conclude, okay, there's a clear difference between the population means in group A and group B. But on the other hand, if it would look like this, so this indicates that we have very little variability within the groups, we would probably conclude that, yeah, there's something going on between the two groups. Group B is, for some reason, on average, performing better than Group A. So the main task of statistics, as how I see it, is to quantify this, this probability that you see here at the top. And there's often, at least in social science, there's often a misconception that statistics somehow takes away uncertainty, but I think that's a wrong way to look at it. To me, it's all about quantifying uncertainty instead of taking it away. So the task is to quantify this probability, and as we will see today, there are several different ways to do that. So the typical approach to this question in the context of hypothesis testing would be, okay, we have these measurements, we have two groups, we have performance measurements. Now we set up two hypotheses. One that's referred as the null hypothesis, that there is no effective group on performance. And then we have an alternative hypothesis that says that there is an effect of group on performance. And now we want to know which of these hypotheses is most likely. And here you might already see a little bit my Bayesian approach to statistics, because this is actually not a question that you're asking if you're a frequentist. So if you're a frequentist, then the only thing you have is a single hypothesis. And again, that's often referred to as the null hypothesis. So as a frequentist, what you would do in this case is compute the probability of the extremeness of the data under the assumption that the null hypothesis is true. So the null hypothesis in this case would be there's no difference in population means between the two groups. And now we can compute, okay, how, assuming that that is true, how, what would be the probability of finding a difference as large as we find here? And again, you don't have an alternative hypothesis. Well, the Bayesian approach, it looks like a subtle difference, but it is actually quite a large difference, as we will see later on. So the Bayesian approach computes the probability of the data given that the null hypothesis is true, and then compares that with the probability of the data given some other hypothesis, an alternative hypothesis. And yeah, this can be one hypothesis, but you could also have a whole series of hypotheses compared with each other. But let's just focus on this binary comparison for a moment. So frequentist, you have one hypothesis, Bayesian, you have two hypotheses, but both of them are based on a quantity that relates to the probability of the data given your hypothesis. So I'll first now briefly give a little bit of history about frequentist statistics. So I won't have time today to go into what I'm showing here on this slide, that there are actually two major schools of frequentist statistics. And I actually didn't know this myself for a long time until I started diving deeper into statistics. And I've noticed that a lot of students, at least here in our department, in our psychology department, are also not aware of it. So if you ask them, okay, who invented the frequentist or the statistical methods that you are using, they often have no clue. They often actually think that it's some kind of mathematical truth and there's only one way of doing statistics. So I think one of the advantages, one of the benefits of also being made familiar with Bayesian statistics is that it will open people's eyes that there's actually different approaches. And as soon as you realize that there's different approaches to statistics, you can also become more critical, because yeah, you don't have to stick to a certain method. There's choices between all methods that you could use. So there's two different schools. So one is invented by Ronald, which is what most people seem to be using, but then there's also another school that's invented by Nyman and Pearson. And it would all be fine if people would be consistently sticking to one of these two approaches to frequentist statistics. But one of the major problems, at least in social sciences, is that a lot of people are using what Gerd Gigerenzer in 2004 called an inconsistent hybrid that every decent statistician would reject. So what's going on right now is that people take some concepts from Fisher and some from Nyman Pearson and mix them together into something that all three of these people actually would reject. So again, I don't have time today to go into this, but if you're interested in learning more about this, then I can highly recommend this paper, Mindless Statistics by Gerd Gigerenzer. It's from 2004, but it's still very very timely. Actually, it's unfortunately not much has changed yet. So, but for today, I will just be sticking to Fisher, which is closest to what most people do and what most people think that they are doing. So Fisher's approach can be summarized in three steps. So the first step is to formulate a null hypothesis. So for example, the drug has no effect on recovery speed, which actually is also something that's as a little bit of a side remark. It's also a bit funny that if you use the frequentist approach, then often you're testing hypotheses that you don't really believe in. Because of course, if you develop a drug, then you believe and hope that it will have some effect, right? But since the frequentist approach is all about falsifying, you always have to specify hypotheses that, yeah, usually you don't believe in yourself. So then the next step is to compute the p-value. And usually now I asked the audience to, if anyone knows the correct definition. And then often there's a long silence until some brave soul dares to speak up and then often gives the wrong answer. But that's the whole point here is to make the audience aware that the p-value is actually a very confusing concept. A lot of people, even at the professor level, often don't know how it's exactly defined. If you're a statistician, you do know, but there's been some research showing that even at a professor level in psychology, there's a lot of people who don't know the correct definition of the p-value. So it's, yeah, the p-value, it's the probability of observing data or more extreme data if H 0, so the null hypothesis is true. So again, it's all conditioned on the null hypothesis. And the other thing to take into account, to note here, is that this more extreme data. So you're not only looking at what's the probability of my data, but also data that you basically haven't observed. And then the third step is, so you have your p-value, then the third step is to interpret your p-value. And in general, it's of course the case that the lower the p-value, the less likely it is that the data were generated by the null hypothesis. So if you have very low p-value, then either something rare has occurred, or it means that the null hypothesis is not true. So one thing to note is that there's no concept of power analysis in this framework. So power analysis comes from Nyman and Pearson, and they actually had quite a different goal in mind than Fisher. And also one thing to note here is, so that's one of the main disadvantages of frequentist statistics in my view, is that a high p-value does not mean that you can accept the null hypothesis. So if you use frequentist statistics, the only thing you can do, you can hope for, is to falsify the hypothesis that you're testing, but you can never find evidence in support of the hypothesis. And one of the reasons is that a high p-value could either mean that the null hypothesis is true, but it could also mean that you just have don't have enough data, for example, that you have very little statistical power, which again isn't even clearly defined in this concept. And that's also Fisher himself, of course. Also, he never pretended that you can use his machinery to find support for hypotheses. He was also very well aware that you can only reject hypotheses. So the reasoning is that the lower the p-value, the more certain we can be that the null hypothesis is false, which on the face of it, it looks like it's a reasonable way to hypothesis testing, but ultimately it's flawed, and not only because we cannot quantify evidence in favor of the null, but there's also something else that's wrong with this, which I'm going to illustrate with a case from England from the late 90s, I believe. So the case of Shelley Clarke. Some people, some of you might have heard of this, but most of you probably not, because you might not even have been born in. Well, perhaps most of you were actually, but it's not been an extremely famous case. I also only started reading about it when I dived into statistics. So what happened is that in 1996, Shelley Clarke got a son, and the son died a few weeks after birth. And then the first hypothesis was that, oh, this is very unfortunate. It was probably a case of, I think the common term is crib death. So it's sudden infant death syndrome, which it doesn't happen very often, but it sometimes happens. But then again, it happened again in 1998. So she got another son, and again, the son died after a few weeks after birth. And then people started to think, okay, this is a little bit suspicious. She has two children, and both of them died. So what's the probability that both of them would die from sudden infant death syndrome? So a criminal case was started against her, and she was actually put in jail on the account of murdering her two children. And what makes this case so sad is that it's partly based on a frequentist statistical argument that, in my view, is highly flawed. So the reasoning was as follows. So we have a null hypothesis, and the null hypothesis in this case is the babies have died from sudden infant death syndrome, also known as crib death. Then what the prosecutor or whoever came up with this argument did was look at how common is this? Is this crib death? What's the frequency in England? And then they found that it's about 1 in 8,500. And then they thought, okay, we know a little bit about statistics. If we have two of them and we consider them independent, which by itself is already a bit of a weird assumption, then the chance of this happening twice is 1 in 73 million, which is a p-value of 0.000137, which you can see here, which is much smaller than 0.05 that usually makes us happy, right? So this would certainly be a paper if these people had been scientists, but not for not for good reasons. So what they did is they rejected A0, and then they conclude, okay, so it was not Sid, so the only thing that we can think about now is that she must be guilty of double murder. And this reasoning, perhaps if you see it for the first time, and you think, okay, yeah, this makes sense. It's very unlikely. But if you think a little bit longer about it, then there's one obvious flaw, right? And that is that they didn't take into account the probability of someone murdering their two children. So they only looked at one hypothesis and they said, oh, this is very unlikely, so the other one must be true. So the point is that even though the null hypothesis is very unlikely here, other hypotheses, including murder, might be extremely unlikely too. So what we can do is actually add murder as an explicit alternative hypothesis. So now we have a second hypothesis, hypothesis 1, double murder. We can do the same kind of exercise, look up what is the infant murder rate, and that's approximately 1 in 33,000 in the UK, which is much lower than the 1 in 8,500. So you can already see where this is going. So if you multiply that, so 1 in 33,000 by times 1 in 33,000, then you'll find a p-value of 1 in 1.1 billion, which is much lower than this 1 in 73 million that we found for the SITS hypothesis. So if you look at it like this, then you could conclude that the SITS hypothesis is actually 15 times more likely than murder. Or perhaps I should say that the data are 15 times more likely under the hypothesis that they died from crib death instead of murder. So the point here is that evidence seems to be best treated as a relative concept. If we try to treat it as an absolute concept, then we run into these very weird kinds of reasoning, especially when we face events that are unlikely under any reasonable hypothesis. So instead of asking how probable is the null hypothesis, as the frequentists do, it seems more sensible to ask how improbable or probable is our null hypothesis relative to some other hypothesis. So it didn't end well for Shelley Clarke. They actually reopened the case with some of this kind of, with pointing out the flaws in their statistical reasoning, and she was set free, but yes, she was so traumatized that she became an alcohol addict and actually died a few years later. So some of you, there's at least one person in the audience who might recognize this case, Weiqi. I don't know if he's nodding, so he recognizes it. So this was a very similar case in the Netherlands, where a nurse I believe she worked in an elderly home. She was convicted because I believe that the case was that the last 8 or 9 people who died in the elderly home all died while she was on duty. So there was the same kind of reasoning that it's very unlikely that they all die, the same person being on duty all the time. And then they also conclude, yes, he probably has had some cause in the death. But for her, it ended better. She got set free, and I think she's living quite a good life now. So the deeper problem here, in my view, is that yes, some events that we're testing are unlikely under any hypothesis that we can come up with, like young children dying. And then, of course, you can wonder, okay, what should we do? Should we reject every hypothesis that we come up with and consider the events unexplainable? Of course, that feels very unsatisfactory, especially as scientists. So one way you could think might solve this is by lowering the alpha value. So usually what you do if you do frequentist statistics, you set some kind of criterion. Often the criterion is 0.05. So you say, okay, if my p-value is smaller than this criterion, then I reject it, otherwise I don't reject it. So you could argue that, okay, for these very rare events, perhaps if we just use a very low alpha value, then we might get out of the problems. And it looks like Ronald Fisher himself also thought along these lines. So he wrote in 1956 that no scientific worker has a fixed level of significance at which from year to year and in all circumstances he rejects hypotheses. So apparently all scientific workers were male in those days. He rather gives his mind to each particular case in the light of the evidence and his ideas. So again, this may sound plausible, but in the end, I don't think this can ever work, because if you want to adjust your alpha criterion based on how rare the event is, then you basically have to know what causes the event, right? But finding out about the cause of the event is the whole reason why we started doing statistics in the first place. So it feels like this would be circular. I don't think this would solve anything. Okay, so I've pointed out a few problems with the p-value now. So the main problems in my view are, first of all, that it's absolute evidence. So it's always about a single hypothesis. And then secondly, we can never support a hypothesis. We can only reject hypothesis. So let's now have a look at the base factor. So the base factor, I actually for a long time thought that this quantity here is the base factor, but that's not true. So what we're looking at here is it's called the posterior ratio. So we have the posterior probability of some hypothesis 0 given the data, divided by the posterior probability of some hypothesis 1 given the data. And as everyone who's familiar with Bayes' rule knows, we can rewrite this posterior ratio to something that looks like this, where we have a prior ratio. So how much do we believe in each hypothesis before seeing any data? And then we have this other quantity, which is often referred to as likelihood ratio, but in the context of statistics, we refer to it as the base factor. So this guy in the middle here, this is called the base factor, and it's the way to interpret it is that it indicates how many times more likely the data are under hypothesis H0 compared to hypothesis H1. So that's one interpretation. Another interpretation is that it indicates how much your belief basically changes when you see the data. So if you haven't seen any data yet, then you only have prior beliefs about the hypothesis. So that's this guy here, the prior ratio. And then you plug in your data, do some calculations, and then you get the posterior ratio. And then the base factor indicates how much more strongly you believe, basically, how much more, yeah, it's the multiplication factor of the posterior ratio. So how much stronger that it becomes.
I have a question, Ronald. So
yeah, sure.
In the Shelley Clarke example, would SIDS and murder base rates be the prior or the base factor?
It would, I actually haven't thought about this. It's a good question. It would probably go in as priors, I would believe. So I have to admit, it's not entirely clear how I would, so I can always use the Shelley Clarke case as a way to criticize frequentist statistics, but I don't immediately see how I would do it in a Bayesian way, because the model is not entirely clear, right? But if there are no data, then yeah, we should go by the prior ratio. So then it would exactly be the answer that I gave before, that the posterior ratio is basically prior ratio, which would be 15 in favor of murder. But of course, you can plug in more data if there is more data.
A way to think about it is it's the prior ratio based on what happens in the world. And the idea is there are people who have the ability to kill their own kids, and what's the probability they do so given that they have the ability. That would give you a likelihood. So you have to have a statistical model of how data is generated before you even talk about a likelihood.
Yeah, that's a good way to look at it. Yeah. Of course, it's a different question how to build that model. It would be quite a daunting task, but formally that looks like a very reasonable approach. Okay, yeah. So so the base factor has a few nice properties in my opinion. So first of all, it's a relative measure. So we always quantify evidence for hypothesis only relative to other hypotheses. Secondly, it has an easy and pleasant interpretation, which, yeah, I personally believe that actually statistics education might better start with the Bayesian approach instead of the frequentist approach, because the Bayesian way of thinking also seems to be much more in line with our intuitive way of reasoning in everyday life. I'll have a small example of that later on in the tutorial. And yeah, so another major difference, the advantage of this approach is that the base factor allows you to quantify evidence in favor of the null. I'll also have an example of this in one of the examples later on, which is something you cannot do in frequentist statistics, which again, I think cripples it a little bit, because it basically means you can only test hypotheses that you don't believe in, or that you want to falsify. And more broadly, this has led to, so this is related to the replication crisis that I talked about earlier. So this focusing on falsifying hypotheses has led to a culture where we really have large disregard for null results. So if we cannot reject a hypothesis, then we don't publish it. And one of the consequences of that has been that something that's called the file draw problem. So there's a lot of failed experiments that we don't know about. So we highly overestimate the evidence that we do actually see, because we don't see the negative evidence. And another problem that it has led to, which Wei Ji referred to earlier when he was talking about toilets and plumbing, is that it has led to very poor statistical hygiene, that people try to do everything in order to find a significant result, to reject their null hypothesis, because that's the only thing they think is publishable. So I think things would be much better if we would have a culture where it's also acceptable to have results that actually speak in favor of the null hypothesis. And yeah, lastly, I think it also generalizes more easily. But again, I'm not a statistician. That's not at all a mathematician, so I don't dare to say this with extremely high certainty. But I think it generalizes more easily than frequentist approach, because of reasons that we'll come to later today. Okay, so here's a visual interpretation. So this is visual interpretation given in one of the papers by Wagemakers. So I'll have a reference in the end of the presentation if you're interested. So he visualizes, or he says that, okay, think about it as if you have a dartboard. Okay, sorry, I should back up a little bit. So what we're seeing here is BF10, and whenever we write BF, it means base factor, and then the subscript means which of the two hypotheses we have on top. So actually this, it would be the inverse of this one. So H1 should be on top and H0 should be at the bottom. And if it's 1, then they're equally likely. If it's 2, then it would mean that the probability of the data are twice as likely under hypothesis 1 compared to hypothesis 0. And then one way to interpret the strength of the evidence is to to think of it as a dartboard. So if it's 1, then it looks like this. Both halves are equal, and then you can think to get some intuitive feel. You can think like, okay, how surprised would I be if I would, with my eyes closed, throw a dart onto this board? How surprised would I be that it lands in one region compared to the other region? Of course, here we wouldn't be surprised either way. So here's another example for 3 1/3. So we would be slightly more surprised if it ends up here in the 1/3 area than in the white area. But yeah, interestingly, I think people actually don't have really good intuitions when they look at the numbers themselves, because from what I remember, this kind of represents what happened in 2016 with Trump and Clinton, that Trump was consistently at about a 1/3 winning probability, posterior probability, consistently over time. So perhaps that also played a role, that people started to believe very, very strongly, like, he can never win. And then the result came in, and everyone was surprised, like, how is this possible? And all the polls are wrong. But yeah, if you're a Bayesian, then you could have seen this coming, and you shouldn't have been too surprised that that happens. Okay, so you can also put some labels. This again comes from a paper by Wagemakers. You can put some verbal labels on the strength of the evidence. Okay, so I think I have 2 more slides on comparing the 2 approaches, and then we'll look at some specific tests. See both of them in actually.
Before you go on, so can you go back to the previous slide? I always have a love-hate relationship with these verbal descriptions, because on the one hand, I feel it's very intuitive to put words on numbers, and it sort of helps create a narrative. But at the same time, it sort of dilutes the power of those numbers, right? Because you are imposing arbitrary categorical boundaries. What do you think about that?
Yeah, I certainly agree. So, because what you're doing here is basically a little bit the same as what has been criticized about the frequentist method, is that we're binarizing results into p smaller than 0.05 and larger than 0.05. Of course, this is slightly finer grained because we don't have, so the equivalent here would be to reject everything that's smaller than 3 and accept it when the null hypothesis is supported by more than 3 points. That would be the exact same thing. So this is a slightly more fine-grained scale, so the problem is not, the potential problems are not as large, but I certainly agree with you that it is a little bit tricky to put these labels, because once you put a label on it, then we don't really consider a base factor of 4 any different from a base factor of 9, because both of them are moderate evidence, and we want to have strong evidence, so we should do a little bit more testing or fiddling around with the analysis. So it is slightly, yeah, it is slightly tricky. But yeah, at the same time, we also want to have some kind of feel of how strong the evidence is.
I also think it depends on field, right? So this is probably representative of psychology, but even within psychology, social psych effects are typically weaker than cognitive psych effects. And then if you go to physics, then a base factor of 100 would be nothing. You would be looking for 10 to the 4, 10 to the 5.
Yeah, that's a good point. Yeah. So these scales, so that's also why I actually quickly skipped over this, because I don't want to put too strong emphasis on on categorizing evidence. But again, if you want to get some feel of it, so perhaps it's useful when you just start using Bayes statistics and you have no good intuition yet of how to interpret these numbers, then it might be a good guide. But yeah, I would strongly recommend to not categorize your results in these labels. Always, yeah, keep thinking about the continuous measure.
Yeah, one thing I wanted to also ask about here is essentially, is there some way of talking about variability here? Because in like things we've seen with like, I mean, more like the hand-built models, but there it often happens that you have, you know, we usually analyze subjects separately, right? And you essentially get some likelihood ratios or base factors and so on for the different subjects. And then you might well have like, you know, a 200 base factor for subject 1 and a -20 for subject 2 and a 30 for subject 3 or something, right? So like we do sometimes see things where it's like much more variable than you would think with these verbal labels, right? Because you would essentially have overwhelming evidence in some subjects in one direction and overwhelming evidence in the opposite direction in others.
Yeah.
Right. So I mean, this is to some degree indicates that our like none of our hypotheses explains all the subjects well, and that's some direction of interpreting this. But this would also put some like if the actual results of separate experiments go so much contrary to each other, this also seems like a bit strange to put that strong labels on those values, right?
Yeah. Yeah, I think I see what you mean, but it might be a slightly orthogonal issue. It's about you're trying to make group level statements about groups where the individuals are highly heterogeneous. So in that case, we should perhaps not even try to make any group level statements. But one thing you could do, and you might even be able to do that in frequentist statistics, I'm not sure, but what people sometimes do in Bayesian statistics is to plot the base factor as a function of the amount of data you put into the analysis. And so one of the programs that is being used a lot for Bayesian statistics called YASP, I'll have a slide about it later, even has a function for that. It's called sequential analysis, I believe. So if you do a t-test, for example, you can click the sequential analysis button, and then you see how does the base factor change as a function of the amount of data points. And of course, if that's very variable, then yeah, you should be much more careful than when it nicely converges to in one direction. Yeah,
I've one thing to add to this. So the problem that you bring up, Heiko, is something that I've been thinking about for pretty much 14 years or so, and it's a very difficult one. So if you believe that all subjects follow the same model or the same hypothesis, then the thing to do is to multiply their base factors and end up with a single base factor, right? And if you don't believe that, or you don't believe that very strongly, then you should do another analysis, and you can still do that analysis in a Bayesian way. You can do hierarchical Bayesian model selection, which is Klaus Ohner-Stefan's method, and that specifically specifies the possibilities that there are subpopulations in your sample and that different people come from different, follow different models. But that's sort of an add-on. Most people would not do that. I think it's always worth trying, even though there are some issues with that method as well. What you can definitely do is report individual base factors and then sort of leave it to the reader to sort of have a visual or vague impression of how probable it is that there's heterogeneity in the population. But all I'm saying is that you are either implicitly committing to everybody coming from the same model, or you're not. And if you're not, then you better make that explicit and do the appropriate test.
Yeah, certainly. Yeah, the problem goes even one step deeper, I believe, that you can even have heterogeneity within a subject, right? You always assume that subjects do the same thing throughout an experiment, but yeah, even there they might be switching between strategies. So that's quite a deep problem. And Bayesian statistics won't magically solve that, of course, because again, it's a bit of an orthogonal problem to what we're talking about today. Yeah, so here's a quick comparison between the two approaches. So in frequentist, you start with formulating single hypothesis. In the Bayesian approach, you always have at least 2 hypotheses, but you can have as many as you want. And then another thing that I haven't touched upon yet is that in the frequentist approach, you have to decide about everything basically before you even collect a single data point. So if you would have a strategy where you say, okay, I'll first collect 20 subjects, and then I do statistics, and then if the p-value is close to 0.05, so which is usually considered as the uncertainty region, then I'll collect another 10 subjects, which sounds like a reasonable strategy, right? Because you say, okay, if the data are not conclusive, I'll just get some more data and to get more certainty. But unfortunately, that's an invalid way of doing frequentist statistics, because the p-value that you will get in the end actually has to be conditioned on the fact that you were peeking at your data after 20 subjects, because you would not have continued the experiment if it had not been close to 0.05. So basically, you're biasing your end result to get down. You will get stronger evidence than you would have found if you had done it correctly. And one of the nice things of the Bayesian approach is that you don't really have this stopping rule problem. I think that the Bayesian approach is still sensitive to some decisions that you make, even though wagenmakers all seem to claim that, no, it's only conditioned on the data. So for example, I think you can still do a peek after every data point and then decide when to stop. I think you will still run into some problems there as well, but it's not as severe as in frequentist statistics. So then step 3 is to gather data. So the point there was that you have more freedom in how you set up your data collection strategy. So then you collect data, then you can compute either a p-value or a Bayes factor. And then again, in the frequentist approach, the usual thing to do is to binarize your results, which I still don't understand why, because unless, of course, you have to make a decision, like what I mentioned earlier, if you work in a pharmaceutical company and you have to decide, are we going to continue with this drug or not? Of course, then you need some criterion to make a decision. But in science, we want to accumulate evidence, right? So why should we ever want to binarize our measure of evidence? But yeah, it's still what often happens. And then in the Bayes in the Bayes thing, you could do the same, but the more typical thing is that you look at the continuous the value of the Bayes factor instead of binarizing it into real or not a real effect. Okay, so this is the really last slide about comparing the two. So p-value evidence absolute, Bayes factor it's relative, p-value can only reject hypothesis, Bayes factor you can reject and support hypothesis. P-value, again, this I'm not 100% sure about it because I'm not a mathematician, but from what I understand, in the frequentist domain, your tests are highly problem specific. And the reason for this, as I understand it, is that since they don't want to deal with priors, which I'll come to in a moment, they have to make tests that don't depend on any latent variables, like a variance, for example, that we don't know in the t-test. So you always need to find test statistics that basically work. But I think the Bayesian approach is much more general in that sense. You can apply it to any problem. And yeah, I think from the literature and from the replication guys, it's clear that p-values are confusing, and Bayes factors might actually be less confusing. I think they're more intuitive. So then you can wonder, okay, why isn't everyone a Bayesian if it's so much better than frequentist method? And yeah, it's not because frequentists think, oh, it's convenient to not be able to support hypotheses. Of course, they would also like to have a way to support hypotheses, but yeah, there are other reasons for it. So one of them is very practical. It's because Bayesian statistics is computationally quite expensive. So you need computational hardware for it, which for a long time was not available. So you could only do Bayesian statistics in very limited, simple settings. But that's not an issue anymore. But the bigger issue is that there's a fundamental difference in how frequentists and Bayesians look at quantification of evidence and how they approach statistics. There's a deep philosophical divide, and it mainly has to do with the specification of prior. So if you're a Bayesian, as everyone who has some familiarity or some experience with Bayesian statistics is that you always run into having to specify priors over variables of which you don't know the value and which you're not interested in computing. So you need to integrate them out basically. And that's something that's frequently say, oh, this is very subjective because we don't have a standard objective way to set a prior. So we don't really want to have anything to do with that because that will inject subjectivity in the results. We want to have something that's objective. So they stay to methods where everything they compute is objective. So very simply put, you could say that Bayesians quantify degrees of belief. So they want to know, after seeing the data, how strongly can I believe that hypothesis A is true compared to hypothesis B, for example. Well, frequentists say, okay, yeah, it might be nice if you can do that without priors, but since you do need prior belief, you need to put in some subjective beliefs in order to come to such a statements. We'd rather want to stay at objective quantities that we can compute. So they look at long-term frequencies of the things they compute. So they don't need to insert any priors. Okay, so this has all been a little bit abstract so far. So I hope at least the people who weren't very familiar yet with both schools, I hope it at least has given some insight and some, oh, hey, Etienne, and some intuition about the differences and commonalities between these two methods, and the shortcomings of the frequentist method and the advantages of the Bayesian method. So what I'll do in the remainder of my talk here is look at some examples. So the first one is correlation. So we have some data here. This is what we see on the x-axis is the presidential height ratio of, I don't remember how many, about 40 different presidents in the US. And the presidential height ratio in this case, it's defined as the tallness of the winning candidate over the tallness of the losing candidate. And then on the y-axis we have the popular support in the general election. And since it's the US, you can have this weird cases where you become president even if you have less than 50% of the vote. So that's these few data points below 0.50. So what this graph seems to suggest is that there might be a correlation between how much support you get in the general election and how much taller you are than your opponent. So these data don't include, because these data are from, I think, from 2015 or something. So they don't include the last, the very last election, but there, that would have been, I think, a little bit of an outlier point. Is the same way as that election has been an outlier in so many ways, because Trump is quite tall, I believe, and he didn't get a large, so he would be somewhere here probably. No, sorry, here. So he would be tall, but still not gets quite a bit taller than Hillary Clinton, but still not gets much more popular votes. In any case, so when we have these data, so two questions that we can ask is, first of all, is there a real correlation? So is this slope that we see, does it represent something in the population, or is it just a property of the sample that we just by chance have some positive correlation here? And then secondly, what we can ask, but this is more a topic for next week, is what would be a plausible estimate of the strength of the true correlation? So the frequentist approach is, it's actually very similar. So the assumptions between frequentists and Bayesians is very similar in a lot of respects, and also the type of questions you ask. It's all about how you quantify the answers to those questions. So what we would do here is assume that these data come from, so these data points are drawn from a bivariate normal distribution, so from a two-dimensional Gaussian. And then if you're a frequentist, you would compute a p-value to answer the question whether the correlation is real, so whether there's reason to believe that that in the population there is a correlation between these two variables. And then secondly, you can compute a confidence interval to get some idea of the plausibility of the range. So one intuitive way of, and this is how I used to think about it, is to think about the p-value in this context is think of it as the probability of finding a correlation coefficient in your sample having a value that's more extreme than, no, sorry, the probability of finding a value that is as extreme or more extreme than what we find. So in this case, it's 0.39, assuming that in reality these data points are drawn from a population in which the correlation coefficient is 0. So this is an intuitive way to think about it, but in reality it is slightly different how frequentists compute this. So what they do is they first compute a t-statistic, and then they look at the extremeness of the t-statistic. So they don't immediately compute the extremeness of the sample and of the correlation coefficient. And I believe this has to do again with what I briefly mentioned earlier, that your test has to be independent of variables that you don't know about. So you first have to transform it to something that doesn't depend on the variance, for example, in the data. So the underlying logic is here that if the true correlation coefficient is 0, then the t-statistic should follow a t-distribution with n-2 degrees of freedom. So then once we know the t-statistic for this particular sample, then we can compute how extreme that the particular statistic is. So in this case, you would compute the probability of t. This should actually be absolute numbers if it's a two-tailed test larger than 0.39, under the assumption that the true correlation is 0. So in this case, if you would do the frequentist test, you would find p-value of 0.007 and a confidence interval, 95% confidence interval of 0.12 to 0.62. And then, of course, you can ask, okay, what did we learn from this analysis? So the first thing that we learned is that if in reality, so if at a population level, the correlation is 0, so there is something in the world that makes taller presidents more popular, we would have only, so if that were not the case, so if it were 0, we would have only a 0.7% chance of finding data as extreme as in our sample. So that seems very unlikely. So it seems very unlikely to that these data were generated by a process in which there is 0 correlation. And then secondly, what a lot of people think they also can conclude from this is that we can be 95% confident that the true correlation is between 0.12 and 0.62. But unfortunately, this would be a Bayesian interpretation of a frequentist concept, because this correlation, this 95% confidence interval, it's again, it's a frequentist concept. And the reason, so one of the reasons why a frequentist would never agree with this is because they don't like to speak even about confidence in your variables having a particular value. For frequentists, either it's in the range or it's not in the range. You cannot say that you're 95% certain. That's a Bayesian interpretation of statistics. But yeah, this is still, I think, the most common way that people interpret it. And again, I think it's intuitively is very appealing. So again, intuitively, I think Bayesian statistics match better with what we would actually like to conclude. It's a little bit the same with the p-value. I think that has changed now, especially since the replication crisis has been so much in the news and students are learning about it. But for a long time, there were a lot of people who would interpret the p-value as the probability of finding something by chance, which again is more closely related to the Bayesian interpretation of evidence, of statistical evidence. Okay, so that was the frequentist method. So let's now contrast this with the Bayesian approach, or I would have to say a Bayesian approach, because since you have to make a few choices, there's a lot of different ways you can, there's a lot of different ways you can do this, and especially the choice about the prior, of course, as I briefly mentioned earlier, but I'll come to a little bit more detail about priors in a minute now. So the Bayesian correlation test, it starts with the same assumption. So we again assume that the data that we just saw, that they come from a bivariate normal distribution. We also ask the same question. So we want to know, is there any evidence that there's for correlation at a population level? But yeah, the main difference, the essential difference, of course, is that we quantify this statistical evidence in different ways. So instead of computing a p-value, we will now compute a base factor, and instead of computing a confidence interval, we will compute a credible interval. So let's have a look again at what the base factor was. So it was this guy here, the probability of the data given one hypothesis relative to the probability of the data under the other hypothesis. So in this case, the hypotheses are R equals 0 or R is unequal to 0. And in here, really what I mean is the population correlation coefficient. So this is of course not the sample correlation, which was 0.39, I believe. So you should read R population here. So what you want to compute is the probability of the data given, assuming that the true correlation coefficient is 0 compared to the assumption that it's unequal to 0. And there's one little problem with this, which we'll see in a few slides from now, but I'll ignore that for the moment. Okay, so let's write our data as pairs of x and y coordinates in this data plot here. Then we can rewrite this to the probability of these two vectors, x and y, given an r equals 0 and given r unequal to 0. So this is what we want to compute here. So I'm just writing the same thing here, and now we can unfold this a little bit, and now we will see. Now we will come to a point where the frequentists would, would leave the room, because this is something they really don't like to see. So what I'm doing here is rewriting both the numerator and the denominator for taking into account that the model that we have. So I mentioned that we assume that the data come from a bivariate normal distribution, which has 5 different parameters, so two means and 2 variances, and there's the correlation coefficient, which I actually wrote outside of the theta factor here. So theta are the parameters of the model. But since we don't know these values, as everyone who's been in Weiji's lab probably knows, is that the way as a Bayesian to deal with this is to integrate over them. So basically what we say is, okay, we don't know what the variance and the mean of these data are. So what we're basically going to do is compute the base factor under every possible value of possible parameter values, and that's this integral here. So far it's still good, but the problem is that probability theory dictates that to do this we have to insert a prior here. So this p of theta is our prior belief in what values the variance and the means in the underlying distributions here could take. And that's something where the frequentists would say, okay, we don't want to make any subjective assumptions about this, so let's do a different test. But yeah, if you're a bold Bayesian, then what you do instead is you define a distribution here, and then you work out these integrals, and then you can compute your base factor. Yeah, so those are the priors over parameter values. I already mentioned these guys will get very, very angry and probably leave the room. So I mentioned in the previous slide that there was another slide problem we have. So, and that's this r unequal to 0, because this is not well specified. What do we mean with r is not equal to 0? So we have to specify that as well, and that means that we just get one more prior, because to do this, we instead of saying r unequal to 0, we integrate over all possible values that we believe r could take. So, and that introduces another prior distribution here. So for example, if we would believe that, if we would have very little reason to believe that there would be any correlation between these two variables, then we could have a prior that's centered around 0. But yeah, if we have no clue, we could have a broader prior, or we might have some reason to believe that there are strong correlations. Then we can put more of the prior mass, so the prior belief about the correlations in the tails of this distribution. But since this is a correlation, and which is bounded by -1 and 1, one very common thing to do here is to assume a normal, a uniform distribution over the entire range. So that you basically don't bias your test to its one correlation or another one.
But even that is a specific choice, right?
Yes.
Uniform is, for example, not invariant under reparameterizations.
Exactly. Yeah. Yeah. So whatever choice you make here, yeah, you have to be aware that it is a choice, and there is some subjectivity to it, and you open yourself to basic criticism. But there are also ways to deal with this. I have one way in a slide coming up in a moment. Okay, so now we have this, and then you could ask, okay, how do we proceed from this, from here? The naive approach would be, which is what I would do as being a non-statistician, I would plug in the bivariate normal distribution here, make up some priors here, and then try to work out the integral there. And I think that would be correct. I don't think there would be anything wrong with that, but there is actually an easier approach, and I might actually arrive at the same thing in the end, but there is an easier approach. So the easier approach is to ask the internet and see what Wagemakers and Rauder and all those other people have been doing over the last few years. And then you'll find a paper that's called a default Bayesian hypothesis test for correlations and partial correlations. For correlations and partial correlations. And what they did there is, from a non-mathematician point of view, it's quite smart, but perhaps it's trivial, I don't know. What they did is they reconceptualized this Bayesian correlation test as a model comparison between two regression models. So what they basically do is they have one regression model that has a 0 slope, and then another regression model that has a non-zero slope, and then they do model comparison to figure out which of these two models receives most support. And then they make also some assumptions about the priors, which is always necessary if you work out a Bayesian test. And they go with something that's called the Jeffreys-Zeller-Simon. I don't remember the names, perhaps Wade knows, but it's a particular kind of prior, which I believe is supposed to be uninformative. But again, whatever prior you choose, you'll always bias your results in one direction or another direction. So even though there's some mathematical definition of uninformativeness, it doesn't mean that we're completely ignorant, or agnostic about the possible values that this can take. So if you follow their approach, then what you get is something that's actually quite simple in the end. You can write it as a closed form solution, and it only depends on the sample correlation coefficient, 0.39 in this case, and the sample size. So it's the same input basically as the frequentist t-test. So if you would have worked this out in the way that I was just suggesting, like plugging in multivariate normal distributions, etc., it might turn out that the variances and means also drop out. I'm not entirely sure, but yeah, since this method has already been developed, just use that one, I would say. I have a slide somewhere about software that you could use where this is implemented. I'm not sure when it comes up. I think it will come up now, probably, yes. So there's two main tools that people use for these statistical. Of course, there are a lot of different tools to do Bayesian calculations, but for these standard statistical tests like t-tests, ANOVA, regression, etc., there's two standard packages that I know of. One of them is called JASP, which is developed by Wagemakers and Rauder and Mori and companions. And the nice thing of that is that, especially for people in the social sciences, that it has a feel that's very similar to SPSS, but much more lightweight, so, and also less confusing. They try to keep the interface cleaner. And another big advantage is that it's free. You don't need to have an expensive license. Yeah, so JASP is actually it's based on a base factor for OR package, which was released by Richard Mori, and I believe that Rauder also has a hand in this package. And yeah, so people who are used to OR, I would really recommend to instead use that package, because it gives you much more control over what you're doing. So like some of the priors you cannot by hand change it in JASP, but in OR I think you have full control over basically everything you want to do. So the examples that I'm going to show a few screenshots of results, they come actually from this JASP software. So the frequentist approach of this presidential hype versus popular votes gave 0.07 and 0.12 to 0.62 as 95% confidence interval. And if we run the Bayesian the test, the one that I just described with Wetzels and Wagemakers, will find, using the default prior, we'll find 6.33. And for the CI, which now is called a credible interval, we find 0.11 to 0.60. So if we do actually find that this 95% confidence interval and the credible interval are very similar to each other. And that's actually, I believe that's the case for a lot of, you'll actually find that very often, but there are also cases, which I'll show an example of in the next slide, where actually you do get find quite different answers. So if you would argue that, oh yeah, 95% confidence interval, I might as well interpret them as credible intervals because they almost always give the same thing. That's not entirely true. You have to be careful with that. And yeah, I don't have time today to go into confidence intervals, but if you're interested in reading about it and misinterpretations of this interval, I can recommend a paper by Richard Morey. I think it's from 2015, which is called something like putting confidence in confidence intervals. Yeah, so what we see here is the result of the Bayesian test that I ran on these presidential height data. So I'll just walk you slowly through this. So on the top, we see the base factors. 1, 0 means the alternative hypothesis compared to the null hypothesis, which turns out to be 6.33, which means that the data are 6.33 times more likely under the hypothesis that there is a true correlation compared to the hypothesis that there is no true correlation. And a BF01 is just the inverse, so it's 1 over 6.33. So it's the evidence in favor of the null, which is smaller than 0, which means that, smaller than 1, which means that it's in favor of the alternative. So these things are just the same. These are the same number, basically. You only need one of them, because then you also don't need to know the other one. So here we have this visual interpretation of the base factor. It can be helpful if you don't have a good intuition for these numbers. And then, so the more interesting part is this bottom part here. And this, now I'm going a little bit into Gianni's part, who will talk about estimation tomorrow, or next week. And yeah, so this is, if I do these tests myself, then this is really the thing that I want to be looking at. Base factors are nice, but in the end, I personally almost always look at posterior distributions as long as they are available. For an ANOVA, for example, it's more difficult to produce them, but for correlation tests like here, we can just as well look at the posterior. So what we see here is, first of all, we see the prior that I used, which is a flat prior of the entire possible domain. So we don't bias our results towards one or another correlation coefficient. And then the solid line that we see here is called the posterior distribution, which is the probability of the value of the correlation coefficients given the data. So here we combine, so the posterior combines the data and the prior into a distribution. You can think of this as a belief distribution. You can think of it as saying like, okay, if I have this prior belief, so in this case, this flat line, and I see these data, so these presidential height data, what would be a justified belief after combining those two pieces of information? So that's represented by this posterior distribution here. So, and what this posterior distribution, for example, shows is that there's very little probability mass to the right of 0, which means that, yeah, there's very little reason to believe that any correlation smaller than 0 is underlying the process that generated these data. And you see the median is 0.37 in this case, which is close to the 0.39, I believe, or 36 that we found as a correlation coefficient in the data. So and the width of the posterior is, you can think of that as a measure of uncertainty. So the narrower it is, the more you put your belief on a very narrow range of values. So the broader it is, the less certain you are about exact values. And one nice thing that you can do based on this on these results is look at, for example, in what range do we find 95% of the probability mass, of the posterior probability mass? And in this case, so that's printed here, so it's between 0.11 and 0.60, which is this credible interval that I referred to earlier. And a lot of people, when they think about confidence intervals, so when they read about confidence interval, they actually have this interpretation in mind. That, okay, now after seeing the data, we can be 90% sure, that 95% sure that the true correlation is within these two within this range. But again, that's a Bayesian interpretation of the confidence interval, which which is wrong, as we will see in the next slide. So this was under a uniform distribution over the entire domain. But let's now say we have some reason to believe that the correlation can only be positive, and then we can run the test again. So the only difference now is that instead of putting the prior over the entire range, we all have it on the positive side here, which brings this automatically to 0, because if you have prior probability of 0, then posterior can never be larger than 0. So all the probability mass is now on the right hand side of 0. And now we see that the base factor becomes stronger, which makes sense because our prior belief is consistent with the data. So then it usually increases. But we also see now that the confidence interval, though actually the confidence interval didn't change a lot, because we already did believe quite strongly in the base test, already did quite strongly believe that it has to be positive. So there was no mass on the left side. But now if we look at the confidence interval, we see something really weird happening. It gets really broad, and it even gets clipped at 1. If you put in these numbers in a confidence calculator, that's not, well, perhaps one that's actually programmed properly, you might even find values larger than 1, which doesn't make sense because it's a correlation coefficient. So I think frequentists need to do some clipping here, which I think is a little bit weird. So this is the last example for the correlation, where I ran it with a negative belief, which after we've seen the data, it's a little bit odd, because we've already seen that the data only give rise to positive beliefs, basically. So we get a really strange posterior distribution here. But this is just to illustrate that the confidence intervals can differ quite a lot. So this now goes from -1 to 0.6. So it's basically covering the entire interval. Well, the Bayesian approach says it's between -0.14 and -0.01. And the reason why we don't have anything positive here is, of course, because our prior says that it has to be negative, which again, it doesn't make sense, but it's just to show that these results can differ quite strongly from each other. Okay, so I have I actually have one test list. I'm just going to do the t-test. Thereafter, I have a few slides about regression and ANOVA, but perhaps we can keep a few minutes for questions. So the t-test, it's actually very similar to the correlation test that we just looked at, but instead of now asking is the correlation 0, we now ask is the effect size 0. So is the difference between these two population means, is there any reason to believe that it's different from 0? So the frequentist approach, it's almost identical to what we did before. You compute the t-statistics, and then you compute a p-value based on the t-statistic and the number of data points that you have. And in this case, we'll find 0.21, which for a frequentist would be a reason to not reject the null hypothesis. But importantly, you can also not use this result as evidence in favor of the null hypothesis. So, and that's again, that's in my view one of the main weaknesses of frequentist statistics. It's if you have a high p-value, you basically can't do anything. You're not allowed to conclude anything. You only can conclude that you cannot reject the null hypothesis. So the interpretation is that if A0 is true, then if you would repeat this, if you would repeatedly sample this many data points from the true population, then in 21% of those samples we would find a t-statistic that is as extreme as our t-statistics, which is not very low. So we should be reluctant to reject the null hypothesis. So again, the conclusion, you can't really conclude anything. So t-test, you can do the same exercise, write down the definition of the base factor, then work it out. Then again, you can just Google what Router and Wagemakers et al. Have been doing. And you'll find a paper. And again, they actually found a nice closed form solution. This looks a little bit daunting if you look at it for the first time, but in the end, it's actually quite a simple calculation. It only depends on the t-statistic and on the number of measurements and the degrees of freedom, but that's just the number of measurements -1 in this case. And this G thing here is the prior. which doesn't have any other parameters. So again, yeah, there's an analytical solution for computing the base vector under these prior assumptions. In this case, we have a Cauchy prior, which is, you can think of it as a normal distribution, but it falls out more quickly. And just to make sure, so this is a prior over the effect size, and the effect size is normalized, so it's divided by the standard deviation. So effect sizes of -2 and -4 are actually, and 2 and 4 are quite big effect sizes.
How did they decide on the default width?
They have some arguments for it, which I forgot. You can find it in this paper here. So perhaps that's the last thing I'll point out here, is that you can, at least in JASP, and certainly also in the R base vector package, you can play around with these priors. So here I have one example where we have the default prior, and we find a base vector of 0.46. So base vector of 2.2 basically in favor of the null hypothesis. So this is evidence in favor of the null. And if we make the prior wider, so if for some reason we believe that there might be a much larger difference between the two populations that we're interested in, we can make it wider, and then in this case we find that the base vector increases to 3.3. And now, of course, this is a little bit tricky, because you can see that, yeah, the base vector, it's highly sensitive to our prior choice. So reviewers actually have a valid point if they ask, okay, to what extent is this robust under your prior settings? So one thing you can do is just look at, if you want to report base values, just to look at, yeah, how much does my result change, my base vector change as a function of the prior setting. So on the x-axis here we have the Cauchy prior width. So the Cauchy has one parameter, one free parameter here that you can play around with. And on the y-axis, we see the base vector. So if the Cauchy prior is 0, it basically means that the alternative hypothesis is identical to the null hypothesis, because you put all your prior width on 0, which is the null hypothesis. So that's why it's makes sense that it's 1 here. And then yeah, the broader you make it, the more evidence you get, in this case in favor of H0. Okay, so ANOVA interrogation, I'm actually going to skip that. So I can put a slide somewhere online so you can have a look at it yourself, and also have a look at the references if you're interested in the technical details behind all these tests. And then I'll just skip to the take-home points. Yeah, so I started with talking very briefly about this inconsistent mix. Sadly, it's widespread, at least in social sciences. But yeah, ultimately, it's a flawed approach, mixing this Fisher and Nijman-Pearson. And again, I couldn't go into detail, but if you want to know more about it, I would really recommend reading the Giger answer paper. Secondly, we have seen that treating evidence as something absolute leads to strange results, like the Shelley Clarke case. So it's better to treat it as a relative concept, and in the Bayesian world, this is automatically the case. Yeah, another thing is that this is perhaps more a personal preference, but I think it makes sense if we have methods with which you can also quantify evidence in favor of a hypothesis. So, for example, it could be useful to show that there's strong evidence in favor of the hypothesis that there's no relation between vaccination and autism, for example. But frequentists don't allow that. You can only reject that hypothesis, so you can only conclude that there is something going on there. Yeah, we also well, this is a bit of a minor point, so I'll skip that for sake of time. Yeah, so the only thing that's so the thing about the Bayesian approach that some people see as a cost, as a disadvantage, is that you have to specify prior. So you have to make yourself comfortable with the idea that you have to put some subjective choices into your analysis. But again, you can, of course, always do robustness tests by looking at how do the results change as a function of priors, etc. And often you have, yeah, I think you can argue quite well for using one prior or another one. And if not, just check the robustness. yeah, Bayesian is quantified belief. So it's really in the end a difference in philosophy. So I very briefly mentioned the replication crisis a few times during this talk, and when I started looking more into the differences between frequentist and Bayesian statistics, etc., then I had the impression that, oh yeah, if you just go Bayesian, then we'll solve a lot of things. The replication crisis, well, it might not magically disappear, but it will help a lot by going Bayesian. But I've actually come back from that a little bit. I think it's much more important to train students and researchers to become mindful statisticians instead of being mindless button clickers, searching for values smaller than 0.05. So if you go from being a mindless frequentist to mindless Bayesian, I don't think there's a lot gained. If you would go from mindless Bayesian to mindless frequentist, I think you would gain actually a lot. And actually, surprisingly, to me at least, it turns out that most people in the statistics department, both in Uppsala and in Stockholm, where I work now, they are actually frequentists. They don't really like the Bayesian approach, but yeah, those people really know what they're doing. Unlike a person like me who is not trained into all the little details of statistics. So for me, I think it's safer and to go the Bayesian way. But again, yeah, just make sure that you have some idea of what you're doing. Okay, so I'll stop here then. And I'm sorry that there's no time for questions. I can hang around for another while, but if people have to go, then of course, feel free.
Yeah. So I think we can take questions. But first, let's thank Ronald. This was really wonderful.
Yes, thank you.
You can raise your hand if you have a question, or you can just unmute yourself and speak up.
Yeah, now it would be useful if we have a host, because I can't see everyone at once. I see some hands, but
yeah, no, so I'm the host, and I can see when people raise their hand.
Yeah, if you can moderate, that would be
sure. Yeah,
nice.
Mike has a question.
I was a little confused by the point hypothesis, you know, correlation 0 versus correlation non-zero. Why can't you condition on correlation 0 absolutely? You make it a delta function. Why do you have to assume some width?
Oh, sorry, perhaps I wasn't clear there. So for the 0, you can assume 0, but for the non-zero, you need to.
Oh, okay. I heard you say something.
Oh, sorry. Perhaps I
contradict that. So I misunderstood you. I'm sorry.
Perhaps I didn't express myself correctly there. No, the null hypothesis is always, at least if you want to compare it to the frequentist statistics, people always use a point hypothesis. But alternative could actually also be a point hypothesis, right? Like, but yeah, that's less useful. More useful would perhaps be to have two composite hypotheses. So you could, for example, test, and that's also one of the nice things of the Bayesian way, that it's all generalized. So you don't have to stick to point hypothesis. So you don't have to stick to hypothesis and say, okay, the value is exactly this. You can compare, for example, the hypothesis that the effect size of my medicine is within 0 and 2 versus that it's between 2 and 5, for example.
Yeah. I also put in the chat, by the way, the frequentist meaning of a confidence interval, which is completely unintelligible, but it is what a confidence interval is.
So one of the reasons I don't include it anymore in my talks is because I get confused myself each time when I talk about it. I don't know anymore how I should interpret it. So for people who have no clue what we're talking about, it's this 95% confidence interval. Apparently Mike put something in the chat, so you can have a look there. But the intuitive way to think about it is that if you would repeat your experiments over and over and over again, then in 95% of the cases, the true generative mean or effect size or whatever would fall within the two bounds. But that doesn't mean that for a given confidence range, you can be 95% sure that it's within same bounds. Because I think you would even need to, you would have to specify prior, etc. You would have to go the Bayesian way. So
no, what I put is it's all the point hypotheses you couldn't reject. So the null is 0, but there are other point hypotheses you could have had that aren't 0, like 0.01 or 0.02 or 0.03, and all of those wouldn't reject. And who cares?
Yeah, that's actually a very good, perhaps a much more intuitive way to think about it. But so one thing, but I'm not sure if there's a question, but one thing I'm wondering about now, if anyone has an answer, I would love to hear it, is what's the use of the confidence interval in the original sense? If it cannot be used to make statements about, okay, we can be 95% sure that it's within this bound, why would you ever compute a confidence interval in the frequentist sense?
Heiko has his hand up.
Yeah, Heiko.
So yeah, two things. I think talking about these confidence intervals. One thing is, I think it gets even like one step worse than what Mike put into the chat for the confidence interval, as in this would be one. And if you now came up with a different test statistic and something else, you would have a different valid confidence interval you could compute. And they don't necessarily have to match up, right? You can compute confidence intervals with a different technique than you compute your tests. So just because you brought it up, like the question, why would you compute this, I think is in a similar sense of the classical statistician, like frequentist idea. You know, you just make, after your experiment, make your absolute statement that like, now I just assume the value is actually in that interval, right? And then I'm right 95% of the time.
Yeah, but yeah,
that's false.
Yeah,
and that's the interpretation how they did it. I think one thing which came a bit short there, so it's more of a comment there, is I think people would also get the credible interval wrong often, in the sense of attributing these properties to credible intervals. Right, so if you like just repeat an experiment many times, and now you now just check how often do you end up in the credible interval, you wouldn't necessarily get this 95% thing, unless your priors are exactly right.
I see
that.
The credible interval is conditioned on the data you actually have, and it's about the data you actually have.
Yeah,
it's exactly, a posterior.
Exactly. And as the confidence intervals are not credible intervals, also the credible intervals are not confidence intervals necessarily.
No, of course, yeah. No, they're completely different concepts. But
for undergrads, a confidence interval, you know, since they're used to frequentist statistics, and when I used to teach an undergraduate lab, you know, I had them do no hypothesis tests. I just had them put confidence intervals on their graphs. But I said, had you wanted to do one, you can always use the rule of thumb of do the confidence intervals overlap, and that's pretty much the test you would have done. So, you know, it's not talking about anything beyond frequentist statistics. It's just a way to make them visible.
Yeah.
So that's, to me, that's the only use, actually.
I have a very practical question. And so if you do your robustness checks on the Bayesian method, on the Bayesian statistics, are they these days acceptable to reviewers and editors, or do reviewers and editors typically still ask you to do frequentist statistics instead or in addition?
Yeah, it really depends on the kind of journal, I think. So in our field, visual psychophysics, working memory, etc., I think Bayesian statistics seem to be quite well accepted. But if you're in social psychology, for example, I think it's less, people are less familiar with it. And I have heard, I've never experienced it myself so far, but I've heard colleagues who had problems publishing Bayesian statistics because either the reviewer didn't understand it, or the editor said, "Oh, readers are not aware, are not familiar with this. We would like to, at the very least, that you also report frequentist statistics." So what often happens is that people report both of them, which I think is fine. And I actually also have done that in, I believe, 1 or 2 papers, that we put the frequentist tables in the supplements. So for even if you have readers who are not familiar or not comfortable with Bayesian statistics, they can always look at the supplements. So that's the safest way to go.
Going back a few years when I used to do motor stuff, and I had a postdoc, Todd Hudson, who insisted on only doing Bayesian statistics because he, you know, thought frequentist statistics were crap. Motor journals, or borderline motor journals, and Journal Neuroscience at that point, but the reviewers from motor papers we're very uncomfortable with Bayesian statistics a lot of the time. So we had to throw in a few t-statistics to satisfy reviewers. My expectation is that's no longer true, but it was at the time.
Right. Maybe it's time to wrap up now. Thanks everybody for coming. The slides and the recording will be posted on our lab website probably under resources. I have Johnny here as well, who's going to do next week's tutorial. Johnny, do you want to say a few words about that next week?
Sure, I can talk briefly about that. Next week, we're going to look at parameter estimation, which is a procedure. It's basically how to do statistical inference before you would do anything like a Bayes factor or hypothesis test. We're going to talk about how to use it by itself without doing hypothesis testing at all. And we're going to go over some of the issues with that, as well as a major focus on how to actually do this in software in Python, so people can choose to use it later if they want.
Wonderful, thank you so much. Thanks everybody for coming. That concludes today's session. Thanks, Ronald, again.
Yes, thanks for having me. It was a pleasure. Always nice to visit your lab, even though I would prefer to come in real life at some point again.
It will happen. It will happen.